Welcome to the next tutorial about computer languages. You got again the PDF with the questions, and now we want to do some explanations of solutions. So let's jump to the first question. The first question uses the state chart which we saw in the lesson, defining a very simple language of one sentence or of one sentence structure where we can create several other sentences from. And the first question directly asks for checks against this grammar, so that we have a special sentence and we want to check if the sentence fulfills the grammar. So the task is check the following sentence with the grammar given by graph if they can be reproduced or produced. So the first sentence is the dog hunts the big fat cat. So let's jump to this state chart and let's directly do the work there. So the sentence was the dog hunts the big fat cat. So let's go. So we are here at this state, and then dog. So here dog is missing. So therefore it does not fulfill the language. So this first sentence cannot be produced with this grammar. Let's go to the next sentence. The next sentence is the small dog hunts the small cat. So let's do this. The small dog, we just follow the lines, hunts the small cat. So that works. So we go this way through our graph and we end up here in an end state. So the second sentence is allowed. Let's do the third sentence. The small barking dog hunts the big fat cat. The small barking dog hunts the big fat cat. You see, we use now this arrow or this edge to the same node, and therefore we can do this. So we do this way, go here, continue, to here, go here, and then to the end state. So there we directly reach an end state and we can process this sentence. So the sentence is allowed. Let's do the last sentence. The last sentence is the small dog hunts the barking fat dog. The small dog hunts the barking fat dog. So let's do the small cat, I think. So let's check. Now dog hunts the barking fat dog. Dog hunts the barking fat dog. So we go again this way, then we do several times here this, and then we continue with this through the graph, and therefore we reach an end state, a defined end state. So there can be several of end states in one graph, so we just have one start state, but we can have several end states in one graph. Also intermediate states can be end state. So for example, if we would have here a double ellipse, then it would also accept the small dog hunts. Okay, so therefore we fulfill this, and therefore the result is that we do not accept this, but we accept these sentences. To accept the first sentence, the dog hunts the big fat cat, we can have a look at it. Let's first of all clean up again, and then let's have a look. And then we need dog, So we need a jump to here, and would have the token dog here, dog, which is this, and then the dog hunts the big fat cat. So only with this additional edge from article to substantive, we would have the acceptance also for this sentence. And this is directly what we want to do in the second part of this question, where we get new sentences, new statements, and we want to add the edges and the nodes which we need to fulfill these. So let's have a look. Extend the state chart so that the following sentences are additionally accepted. The nice cat hunts the fat dog. So what do we need? Let's go back to this graph. So let's start the, and then we need nice. Well, so we don't have it here. So one way is to do this, to add an additional edge and write nice to here, so that this is an additional edge. It's just not allowed that you have more than two edges with the same token or with the same letter code, so that you have two possibilities to go the same way. It's allowed to have several different arrows or several different edges, but they must have different labels on that. Similar to that would be to add an additional or here and to add this label directly on this edge. So nice to here. This means that we can represent it with an additional edge or just with an or on an existing edge, which is similar to an additional edge. And then we can follow the nice cat hunts the fat dog. So this is our way that we can accept this additional sentence. Of course, this extension allows additional sentences, so we do not just only support this sentence which we wanted to support. So possible is also the nice dog hunts the barking dog, and the small the nice small dog hunts, and so on. So all of the possibilities which we can now create are allowed now. And the only thing is, if we want just this, then we have to create a complete new path, so that we cannot jump back to an existing thing. So if just the sentence, the nice cat hunts the fat dog, should be allowed, then we have to create a completely different path through this graph. Let's go to the next sentence. The next sentence is the nice cat hunts mice. So let's do this. We need again this nice here. Cat hunts and then we need mice. So therefore we can go this way and give the label mice here. So this is one possibility. Of course, you can also do another way, so that you don't use this, and that you have an additional end state, for example. So let's do this as well. So we have hunts and then we can go to a completely different position. We make a new state in this chart, a new node, and we define this as let's say sub2. Okay, and we write mice onto this label. So this is also a completely valid graph, so that we have another way now, but it's always the same style, so that we can follow this direction and go to here. Okay, so it's exactly what we need. The nice cat hunts mice. Let's go to the next sentence. The next sentence is: the small dog hunts the fat cat. So let's do this here. The small dog hunts the fat cat. Oh, it's already accepted, so we don't have to change anything. You should keep this in mind. For example, I do this sometimes in the final exam, so that I see you understood really what you do, because sometimes it's also possible not to change things, so that this is also a point for you. Okay, so don't be too shocked if you don't have to do things. It just tells me that you're able to do things. Okay, and then let's go to the last sentence: the small cat hunts, which is in principle already what we explained for the first task. The small cat hunts means the small cat hunts. So there are again two possibilities. We can create an additional end node here, or we just make an end node here. So it's not necessary that you have always separated nodes. So you can continue from an end node, from a final node, to a next one, but it just tells you that you are allowed to stop here. So the small cat hunts is a correct setup, because it tells us that we can stop here, and if you reach an end state, then it's accepted. So let's continue with the next question. Next question deals with the more complex grammar, with the context or context-free grammar, which we heard in the lesson about checking of regular mathematical expressions, so that we have mathematical equation systems using braces and things like that. This is the ETF grammar. So let's do that. Given is the ETF grammar. This ETF grammar is defined by ETF with a terminal symbols plus multiplication sign, parentheses open and close, and ABC to set. Symbol E is the starting part, so that we start with E, and then you have the classic ETF grammar here. Draw the production tree to create the following expression: A plus B in braces times B plus C in braces. So this means we cannot change the order here. So we do a real lexical check, which means we check the grammar. So it's mathematical, you would be able to change this, so that B plus C can be in the first position, A plus B can be in the second position. Again, here in the lexical check for the grammar, we cannot change anything here. So let's directly start this, and I switch to my external camera. So we want to create the statement A plus B times B plus C. So in the ETF grammar, we start with E, of course, and then the next step is T. Remember, the ETF grammar looks like this. So what we do, we go from the E to T. This is the first jump. And on the way to this statement, we now go from T to T times F. T times F. Well, this multiplication sign is already part of our final, of our terminal symbol alphabet. So we need this multiplication sign, therefore we create it. And then we continue. T can be again replaced by F. So we have F times F here. And then F can be replaced by this parenthesis sequence. So that we have E times E in parentheses. And then we use E plus T times, so in each of these sentences, each of these statements is a complete part, a complete set of terminals and non-terminals where we replace the non-terminals in the next step. So E must be replaced again by T, and T must be replaced again by F, and then F can be replaced by A. Okay, so, and then we have the plus, we keep the plus, so T can be replaced by F, and F can be replaced by B. So we have this scenario, and the same here. E replaced by T, T replaced by F, plus T replaced by F, F, and we go to here. So with this, we created the complete construction tree of our grammar. Let's jump back to our question sheet. The next question does something with Turing machines. So what you should train is a little bit the use of state machines. And therefore you should play a little bit with this, what is a Turing machine, to run through a state machine, and you should create your own state machine. Therefore question 3 and question 4 a little bit plays with this stuff. So let's go to question 3. Remember the Turing machine for adding 1 to a given binary number, and write the complete path through the automation when 1111 is printed, where the number sign or this hashtag is used as a blank symbol. So the type of this Turing machine is represented from the lesson like this. And then what we do is we start with a starting tape, and then we just follow the rules here. So we don't paint the graph, we just follow the rules here. Let's do this. So we have this scenario. These are our rules, our transitions, or our edges between the nodes. And then we want to start with a special given tape. So the tape in our case starts with this. We have the 111 on the tape, and we have on the left and on the right an infinite number of blank symbols. And then we are on the first position. We always start on the most left position, and we are in the state 0. So what is the next step? If we are in state 0, this is our start state as well. So if you are in state 0 and if we read a 1, then we go to state 0, write a 1 and go to the right. So we keep the state 0, we write a 1 here and go to the right. So the next step looks like this. And we are now at the second position, but we are in the same state. So this is the same rule again. So the next step looks again like this. And we are now at this position. And it's the same rule again. So the next step looks like this. And now there should be a change, because we are in state 0, but now we read this hashtag. The hashtag or number sign, how you want to call it, So this hashtag follows that we changed the state. So we change to state 1. We write the hashtag back and we go to the left. So the next step looks like this, that we have a 111. Still a hashtag here. We are now at this position because we went to the left and we are in the state 1. And now in state 1 there's a difference. Now we have a change. So we now read a 1. If we are in state 1 and if we read a 1, we are here. Then we change to state 1 and write a 0. So that's this. So we have now 110 because we wrote a 0 and we go to the left. So we are now at this position with the same state. Okay, we have again this situation. So the next step looks again like this. We have 100. We replace this with 0 and we keep this state 1. And we have this same situation. We read a 1 and we go to the left. So we transform it to a 0 and we are at the left position but still in state 1. And now we have a change because now we read another sign. We read the blank symbol. So the blank symbol turns directly to this state. So we have now this situation, which is also our final state. We replace this by a 1. So we have a 1. And then we have 00 and the hashtag. And we keep neutral. So we are on the same position and we change into the end state. So this is our end state. So this E. And therefore we have now this situation. As we have an infinite set of blank symbols on the left and on the right, it continues of course with this blank symbol, and therefore we changed from this. Sorry, I missed here 10. So we changed from this here to this, and this is exactly 111 plus 1, which is 1000. Okay. So therefore we have the complete run through our states following the rules. And the next question deals with the conversion from such a rule set into a state chart. So let's go to that. Draw a state diagram for the following Turing machine, which converts unary number presentation like 5 bars for the decimal number 5 into a binary representation like 101 for the same decimal number. There is a short hint. Task type could be similar with changed Turing machines in the final exam, for example. So let's do this. So let's do the painting here. We start with S0. So this is our start state. So therefore we have a node S0. And from this node S0 we have a change to S1. So we have a node S1. So on the first change here from S0 is the following. So we read a 1, and now I mark the read and the write and movement with this double slash, and we write a X and go to the left. So this is the first change. And then we have a change to S2. So we need an S2. And this change to S2 is the following. So let's have a look here. So we go from here to S2 when we read the blank symbol, and we write the blank symbol and go to the left. And the next one keeps S2 state. So in the next steps we always keep the state S2. So we have 3 loops to ourselves. It looks like a flower. So, and the first one is we read a x and we write x and go to the right. And the next one is we read a 0, we write a 0 and go to the right. And we read a 1, we write a 1 and go to the right. So this is the complete setup for S0. Then we are in state S1. In state S1 we can go back to S0 again. So we have two possibilities to go back to S0 again. So this one and this one. And the first one is we read a number sign, we write a 1 and go to the right. And the next one is we read a 0, we write a 1 and go to the right. So, and then we have two states where we stay in the same position. So again we paint a nice flower and we do a reading of 1, write a 0, left. And we read a x, write an x and go to the left. So these are our steps. And then we continue in state S2. So we have this situation. In state F2 we can change to state 3. So therefore we need another state. Let's paint it here. So the state S3. In the first situation we keep the position. So we do this. And we read an x, write the blank symbol and go to the left. And then we have two positions to come to state 3. So it's this. And this means in the first one we read a 1, write a 1 and stay neutral. And then the next one we read a 0, write a 0 and go neutral. And therefore the graph which we have looks like this. We have 4 different states and we have the interconnections which are the transitions or the edges defined by these rules. This is question number 4. And now let's go to the final question. The final question deals a little bit with the problems you will have to remember on numbers or times or whatever. So you should create the state diagram for a traffic light. And for a traffic light you need an additional information. So let's first of all do the state diagram for the traffic light and then let's discuss why this is not so ideal. So the question is create a state diagram for traffic light when the following situation sequence is given. So you have red, yellow, green and yellow. So these are the 4 different states of our traffic light, and therefore we can of course directly convert this. So let's go to our external camera and then we know we have 4 states. So we have the situation where only red is colored. Then we have the situation where red and yellow is colored. Then we have the situation where only green is colored. And then we have the situation where the LED for the yellow is switched on. So, and we have transition between this. Which tells us the steps. So in this case we have to switch on yellow. In this case we have to switch off red, switch off yellow and switch on green. So maybe I have to paint it a little bit more visible. let's continue with the transitions. From here to here, we switch off the green and we switch on yellow. And from here to here, we switch off yellow and we switch on red. So we have now trigger points at this nice diagram. So it just continues and follows. We have no trigger points. So if you remember, in the classic language diagrams, we have a trigger point which is reading a character and then doing the transition, or for the Turing machine, reading a character and then doing activity, memory access and things like that. Here we just have the activity and now trigger point. So therefore, a trigger point would be the time. So this is what you cannot represent in a state chart in this point. So you can make a question. So time is 10 seconds or something like that. So that you have now a definition, but this time is an external memory. So and therefore you need an external memory for that. But you can represent, of course, the different states, but you cannot directly define the timely sequence and the timely behavior. And this is what you should see here at this question, that you have the states, but you have not the sequential behavior. And in one of the next lessons, you will see other diagrams, for example, in a unified modeling language, where you can also define the sequence through a special behavior according to the time behavior, or the behavior in timely sequences. And therefore, the state chart really just describes the different states and the transitions between the states. So that's it for today. We solved our tasks. We see each other again in the next lesson. So therefore, stay safe and have a lot of fun with next tasks and all of that things. Bye bye.